And because you have this inner product, this means there's a Clifford algebra, which is just a quotient of tensor algebra by a relation involving the inner product. Okay, and this Clifford algebra acts very naturally on the differential forms of M. And how do you do it? Well, you take a vector part and a one-form part, and you act on some differential form. You just contract the vector part, and you wedge the differential form part. Okay. And the other piece of information here is this differential operator, the exterior derivative. And if you have these two things, you can get a bracket on T, similar to the way you would get a Lie bracket. So this is supposed to be some element in bold T, and you get it by acting on a differential form. And this will be a commutator. Like so. And we can write down this bracket. So what do? You just take the Lie bracket of the vector parts, and you differentiate in the x direction, and you almost differentiate in the y direction, but not quite. Okay, and this is the Courant bracket. And finally, there's one little modification you can do if you have some closed 3 form. You can modify this differential, this operator, by just adding wedging by h. And the result will be a slightly different bracket, an h twisted bracket, where you contract y and x into h. Okay. So all of this data, the bracket, the inner product, and one more thing, give a Courant algebroid. So the final thing that you need is to notice that if you have some section of here, you can act on functions just by projecting onto the vector part. Okay, and so this is the data of an exact Courant algebroid. And so the next step is if you have some vector bundle over M, and you want to lift this action of bold T onto this vector bundle, you need some idea of a connection. So what is a generalized connection? So it's just going to be some operator taking sections of this vector bundle to sections of bold T dual answered with the vector bundle. And it should satisfy a Leibniz rule, the usual thing. You can act on F, of course, and then also you can act on S. Okay. And so, well, what are these things really? Well, this tangent bundle projects in 2 ways, onto T star and onto T. And so this connection decomposes into 2 pieces. One being an actual connection on V, and then you have this chi, and chi is a section of T tensored with the endomorphisms of V. So we think of this as a vector field. It's a vector field valued in endomorphisms. Okay, so this is one interpretation of what a generalized connection is. And there's another one that comes when you have a generalized metric. So as we've seen, this space already has this split signature metric, but a generalized metric should be something positive definite. So the way that we get such a thing is we just take a maximally positive definite subspace, or subbundle rather, of bold T. Okay, so the picture. There's some color I'm not supposed to use, right? Orange. Orange, okay. So you have T and you have T star, and sitting inside here you have, actually let me not call it V plus, call it C plus. You have C plus, and because it's positive, maximally positive definite, it tells you there's a map going from T to T star, for which this is a graph. And the map is gonna, so it's the two tensor, it's gonna have some symmetric and an anti-skew symmetric part, which I'll call G plus B. So I have C plus is just the graph of G plus B. And so, yeah, rather suggestively, G is actually a Riemannian metric. So you do get back a Riemannian metric, but you have this sort of pesky 2 form kicking around as well. And well, fortunately, you can get rid of it, but there's a sacrifice to be made, and that's that you have to move around T within this space. So you can't care about the general presentation as some direct sum. You have to sort of deform T by some gauge transformation, e to the minus B. And then C plus, then you eliminate the B term. So you can gauge away B. Okay. And so in addition to C plus, if you have this maximally positive definite subbundle, you can also take its orthogonal complement, C minus, and this will be a maximally negative definite. And before you've done the gauge transform, at least it looks like the graph of B minus G. Okay. So you have these two spaces, and they project isomorphically onto T. You have some projection. And so you have another decomposition of this operator, nabla, into nabla plus nabla minus. And so this new reinterpretation is that that this generalized connection is really a way of carrying around the data of two connections. Okay. So what can you do once you have a connection? Well, you take its curvature. And the naive formula is just the failure of this action, this lifted action, to be a courant action, if you like, to respect the courant bracket. And this is the courant bracket. And so this is all fine until you realize but there's an issue. This thing is not tensorial, in particular if you plug in a function. You get chi, the vector field acting on F, times this inner product of U and V. But it's not all that bad because it turns out to be tensorial in the second argument. Okay. So what does this mean? Well, it means you can reinterpret this, this curvature as an operator. So we're going to have an operator D from sections of T, answered with morphisms of V. And how do you get this thing? Well, it really is the same thing as R. Once you just contract where you're allowed to using the inner product. And this first equation tells you that this is a first order linear differential operator covering this vector field chi. Okay. The picture is like this. You have, it's not skew symmetric, no. Oh, sorry.
By
yes.
definition.
My current bracket was not skew symmetric.
It's
It's
the other one.
Skew bracket. Yeah.
Okay.
Okay, so you have this generalized tangent bundle over M, and the picture is, so this differential operator, this first order linear differential operator is really a vector field on the total space. So you have some. And this vector field covers some vector field on M. Okay. And one thing you can do with this vector field is you can use it to sort of drag around your generalized metric. You can, you could take some flow and you can move the generalized metric in some direction. And this is not all that interesting until your curvature depends on the generalized metric. So how do you get these things? So actually, first I want to give an important special case. So far, there's an objection that should be made, and that's this is not really a vector field. It's a vector field valued in endomorphisms of V. So what you do is you restrict to the case when V is a Hermitian line bundle. And you take nabla to be unitary in the usual sense. So I just mean that some section U acts on this Hermitian metric as a derivation. Okay, and in this case, the vector field you get is really a unitary valued vector field, or in other words, it's just an imaginary vector field on M. And this differential operator D, or if you divide by I, you get a differential operator from T to T. So you really do get a vector field in this case. Okay. So let me show you how, for the rest of the talk, I'll give it an example of how you get one of these line bundles coming from a metric. So this all takes place in the setting of generalized Hermitian or generalized Kähler geometry. What is a generalized Hermitian structure? You have some manifold, you have a generalized metric, and you have a generalized complex structure where you have some compatibility between the two. And so what is this generalized complex structure? It's supposed to be preserve the pairing on bold T, and it squares to -1. And moreover, you need some integrability condition. Which I'm not going to go into. And so what do you get in this case? Or actually, maybe, yeah. So what do you get in this case? Well, the spinors, the differential forms on M, they decompose because of this J operator. This lifts to a circle bundle on the spinors, and a circle action, and these differential forms decompose into eigenspaces for this circle action. And this first one we call the canonical bundle for J. And this canonical bundle has the structure. It has, first of all, it's generalized holomorphic. For J. And secondly, so the generalized metric on M gives you a metric on the differential forms. We're used to this, and then you can restrict this thing to the canonical bundle, and you get a Hermitian metric on K. Okay, and together, this is enough to produce what we need. So in complete analogy to the classical theory, you can use this generalized holomorphic structure and the Hermitian metric to produce a connection, a generalized connection called the generalized Chern connection, which is just, it's the holomorphic structure plus the anti-holomorphic structure on the dual. Okay. And so then what do you have? You have a unitary connection, unitary generalized connection. On this Hermitian line bundle. And so you can use it now to move around your generalized metric, but in fact, it depends on the generalized metric. So you get this PDE on these generalized metrics. And this is one way of producing the generalized Kähler-Ricci flow. So these generalized Ricci flows first appeared in the physics literature in terms of some renormalization group flow, and then they've been receiving increasing attention from people like Jeffrey Streets, work of Jeffrey Streets, Mario Garcia Fernandez, and Pavel Javera, many more people as well. Okay, I will stop there. Thank you.
Thank you, Caleb. Is there any question? Chen Chang?
So we know like connection of Lie algebra. Lie algebra is introduce representation up to homotopy, right? So
Yes.
how about your connection of this capital T will it introduce representation up to homotopy of Crouch, right, or something like
I
that?
have not looked into that. It's, yeah, I'm not sure. It's a good question.
Any other question or comment? If not, let's thank Caleb again